Hello, my name is Robert Stewart, and my capstone project focused on attempting to recycle elastomers through the use of chloramines. A little bit of background on how I got my project. I was a student in this professor's class last semester, and I was very interested in the material that he was using for his class. In addition, the research that he mentioned he did on syllabus day and other days earlier in the class piqued my interest, and so I decided to bring an idea to him of a potential capstone project. During that meeting, he discussed this different project that he had the materials and idea to do, but he did not yet have a student that was able to perform this experiment. As such, I was able to take this project that I'm presenting today and make it into my own and to use it as my capstone experience. More information about the project itself. As you would know, a big focus in waste management today is about dealing with plastics, whether it's reducing their use or recycling them or just reusing them overall. This focuses specifically on recycling. Recycling plastics is a difficult process, and the most commonly recycled plastics are something called thermoplastics. These have very linear chains, partially as what's seen here, but the difference between this graphic and thermoplastics is that they do not have these links between the chains. The lack of these links means that you can just heat them up and either melt or soften them and then reform them into a new product. This does degrade their mechanical properties a little bit, but it enables very easy recycling. Elastomers are very different. Elastomers also are represented by this graphic, where they have these chains, but then they have links between them. This isn't a perfect representation of elastomers, as in a elastomer, you'd only have bonds between different chains. You would not have this additional atom or molecule, yet this is still a very good representation. The addition of these bonds means you cannot just melt or soften the plastic that easily, and so it makes recycling of elastomers much more difficult. You need to find a way to preferentially break the bonds between chains. Within the last 10 years or so, there's been specific research into this issue, and it was actually found that in some wastewater treatment plants that used monochloramines as a disinfectant, that the rubber seals were degraded more rapidly than in plants that weren't using these monochloramines. This degradation was then looked into and replicated in labs using these very low concentrations of solutions that you would find in the wastewater treatment plants. A different study then took this a step farther and used much higher concentrations of chloramines to attempt to speed up the degradation process and was able to completely degrade a sample of elastomer. For this project, I wanted to both replicate these experiments as well as take them a step farther and try to do a characterization of what I was able to extract through resin. So as you can see in this graphic here, I've laid out the different steps of performing the degradation experiments. First, you need to add some of the monochloramine solution to an elastomer. The elastomer is represented by this bar. Next, you heat it up to about 65 degrees Celsius and wait 24 hours. Now, every 24 hours, you need to replace the monochloramine solution because chloramines are very unstable and will decompose as they are heated. As such, every 24 hours, I took the spent solution and collected it in a collection jar as it contained bits of elastomer or resin. And then I refreshed the solution with a completely new batch. This then repeated for several days until I felt that I had collected enough resin for my purposes, or that I was able to see enough degradation. Unfortunately, I was not able to see any significant degradation with the low concentration trials. I was able to determine this through something called swell testing. Swell testing is the process of taking some kind of elastomer, such as a rubber band, measuring its volume, and then submerging it in some kind of solvent, waiting for about 2 days to make sure it's completely saturated, and then measuring its volume again. This change in volume allows you to determine the cross-linking density, which is defined as how many crosslinks like this are present in the material within a certain volume. So for these low concentration trials, this cross-linking density did not significantly change, and so I moved on to the high concentration trials. With these trials, those are still ongoing, so unfortunately I do not have solid results. However, I do have some evidence that degradation is in fact occurring. As you can see down here, these two larger vials started very clear, and then the next day they are much cloudier. This represents that something is going on, whether that is degradation or just additives being leached out of the polymer is unknown. However, I am inclined to say that this is actually degradation, as you can see some particles coming out of this solution. You cannot see the similar degradation in these vials, as they are, first of all, full polymers, full rubber bands. The chopped bits of rubber band here and the chopped bits of tire have a lot more surface area, and so that allows more of the chloramine to attack them. And also, I was able to stir the samples with chopped rubber bands and chopped tire, whereas I was not able to do so for the full rubber bands. This also increases the amount of contact between the rubber band and the chloramine, which would increase degradation. Overall, the lack of degradation in the low concentration trials means that the low concentration solutions are not feasible for use in recycling elastomers. This is fine, however, because there has been color change, like I mentioned, in the higher concentration tests, and so degradation is probably occurring. However, I do need to still collect more data to ensure that this is the kind of degradation I was expecting. As I still have this trial ongoing, my future research will involve finishing these trials and performing the characterization of, one, the cross-link density using this well testing that I mentioned, as well as attempting liquid-liquid extraction on the collection solution, where I can extract any kinds of resins and particulates out of the water into an organic solvent such as hexanes, which are much more easily vaporized off. This would then allow me to identify the composition of the recovered resin after I have removed all the hexanes, and I could attempt to recross-link what I recovered to see if I can form it back into a usable project of elastomer. Overall, I've learned a lot from this project. I have gotten a lot of experience of planning an experiment from the beginning to the end. I did see some delays as the degradation process is a very long one, and so any small hiccups, such as waiting for a material to arrive or other people using the equipment that I would need, cause a large delay in my process. I also learned how to do this well testing, as well as got more practical experience with doing liquid-liquid extraction, as well as rotovapping samples. That is my experiment, and thank you for listening.